What I'll speak about is try to tell a simple story about exciton-polarons and how we can use them to distinguish the layer, the valley, the spin, the properties of different correlated states in these moiré heterostructures. So I have sort of three simple messages. One is the exciton-polarons, which Atacha introduced yesterday. Here we won't be looking at their interactions with each other, but rather looking at how they can be used as probes. And as I said, they can probe the spin, valley, and layer degrees of freedom in a heterostructure. And they're very valuable to sort of untangle some sort of complications that arise in strongly correlated states. And then the final thing is we'll apply this to a hetero-trilayer where we observe field-tunable correlated states that we find are best described by a sort of multi-orbital Hubbard model. So first, I'd like to thank the guys who really did the work. So it's really been a team effort between Aidan, Mauro, and Hunjun. And this is primarily work I'll be talking about today from Aidan's thesis. And we get invaluable support from Johannes's group for theory, and also our Japanese HBN collaborators. So I guess everybody will know this schematic. So as you thin down a transition metal dicaucagenide, it becomes direct band gap at the K points, and what happens as you thin down is you basically suppress the interlayer coupling, and that pushes down in the valence band, in particular at the gamma point. And so you have these sort of p-type orbitals on the chalcogen atoms that directly lead to this interlayer coupling, and when you get down to the monolayer case, then you have a direct band gap. But as the heterostructures get more complex, you can have a competition between these different states in these different valleys in the valence band in particular, and as well as in the conduction band. So one nice example of sort of tunability in this system was done a few years ago in a tri-layer tungsten diselenide. This is measured in transport, where they looked at the effective mass of the carriers sitting in the gamma valley or in the K valley, and what they had is this tri-layer device. So the ground state is in the gamma valley to begin with, and as you can see, the population is primarily in the gamma. And then as they apply an electric field, they can sort of tilt the polarization, so you get sort of layer polarized, and you can move the K valley relative to the gamma valley. And in this case, then the carriers move into the K valley, and so you have this sort of field-induced tunability between the two bands. And we'll use this sort of trick later. And as well, at the K points is where you have the optically active excitons in sort of momentum direct. And I think most people are quite familiar with this picture. So you have these very strongly bound excitons, and they're very susceptible to their environment because they have such a sort of a strong dependence on the dielectric environment. And we'll take advantage of that later as well. In addition, when you then take these excitons and you sort of immerse them in a Fermi seat, you get these new sort of many-body states appearing. So this is an example from the Zurich group a few years ago. So here's a gated sample of monolayer molybdenum diselenide, and you have this intrinsic region. So this is looking at absorption spectroscopy or reflectivity of the sample. So you have a neutral exciton, and when you overcome the intrinsic region, either N-type or P-type doping, you have the emergence of a repulsive polaron on both types of doping, and then you have the emergence of a so-called attractive polaron in this case. This sort of in this binding energy is sort of commonly referred to as sort of the trion binding energy for the bound state, but it's really sort of a mini-body feature. And there's lots of interesting things about these exciton-polarons or Fermi polarons. What I'd like to discuss today is sort of using these many-body states as probes of the different types of states in terms of the doping. So to do that, I'll give an example on a gated 2H bilayer tungsten diselenide. So this is untwisted, just naturally exfoliated. And what we can see is we have an intrinsic region where we have the neutral exciton, we have the repulsive polaron branches. I don't know how well it's showing up out there. And then we have the attractive polaron branches for both the conduction and valence bands. And so if we first look at the case of the valence band, so we see that there's a blue shift with increasing carrier concentration, and this is arising due to phase space filling. So you can imagine we have our excitons probing the K valleys, and as we start to dope the system, then we have to go to higher momentum to find a hole to be absorbed, and that's why we get this blue shift. On the other hand, if we look at the conduction band doping, we see that we have these attractive polarons with a redshift. So we see the strong initial redshift. And this is because we lack phase space filling. In this particular sample, it turns out the ground state is not at the K valleys, but rather it's some sort of hybridized gamma or Q valley between the two layers. Well, the wave function is extended across the two layers. And in this case, we don't have the phase space filling, and there's some sort of non-trivial many-body effect that renormalizes the energy, and you get a red shift instead of a blue shift. So in addition, there are other signatures that can arise if we turn on a magnetic field. So we have strong spin polarization of the exciton-polarons when we are dealing with K-valley doping. And if we're dealing with excitons probing the K-valley and the doping somewhere else, we have very or almost no spin selectivity. And so I'll give an example of that here. So here we take the same sample, and now we turn on a magnetic field of 5 Tesla, and then we look at this polarized light, so the helicity of the light, so sigma plus and sigma minus. And what we can see is there's a large change in the turn-on energy of the attractive polaron, the bias that we need in these two scenarios, and that's because you can imagine our Fermi C sort of is sitting somewhere, Fermi energy sitting at sort of this energy here, and we separate the two spin levels in the system, and we have this strong turn-on bias. On the other hand, in the conduction band, you see there's almost no change. And this is because we're doping into a different valley, so there's no change in the energy. As well, the position of this peak has changed greatly, these two peaks, and that's due to the G factor. And we can plot this G factor as a function of the carrier doping. So we see for the attractive polaron in the case of the negative charge, in the conduction doping in the conduction band, we have basically the same nominal G factor we expect for sort of neutral excitons in the system of about -4. But in the valence band, we have a very different G factor that arises due to some sort of parametric coupling in the valence band that we won't talk about today. But nevertheless, the sort of idea then is we can use these Fermi polarons and use them as spectroscopic tools. So the first thing is we have the sensitivity of the excitons to the dielectric environment, so that changes the energy of the system, of the exciton. We have the phase space filling effects for K-valley exciton polarons, which doesn't appear for the doping into other valleys. And similarly, we have these strong magneto-optical effects for K-valley exciton polarons. So with this knowledge, then, we can sort of apply this to our sort of slightly more complex heterostructures then. So I won't introduce this very much. I'll just sort of mention that you know, sort of the idea of the Hubbard model is very trivial, at least to write down a Hamiltonian for. So you simply have an on-site Coulomb interaction energy and carrier hopping between different sites. And if U is greater than T, then these strong correlations emerge. And then you can have another term here for longer range interactions that can lead to Wigner crystals and things like this. So the sort of simple picture of a Hubbard model is the case where you have sort of the Coulomb energy is large enough that it pushes the hopping to the next site outside the unit cell, let's say, and you have this sort of picture where you have then the emergence of an upper Hubbard band and a lower Hubbard band split by this Coulomb interaction energy. But there are other types of materials and other types of models where you can start to think about then if you have some other band that is sort of in between the energies of the upper and lower Hubbard band, where you can have carrier hopping into these other sites in space within that unit cell. And these are often called charge transfer insulators, and they're sort of a slightly more complex Hubbard model is needed to describe them, but they're quite relevant. So, for instance, a lot of the cuprates, these high TC superconductors, the best models normally start from some sort of multi-orbital Hubbard model to describe them. And of course, 5 years ago or so, my math is bad, it's more than 5 years now, Alan MacDonald and several other theorists not long after realized that these TMDs can offer a very nice Hubbard sort of model, especially in the valence band where you have the strong spin-orbit coupling, and it can be a very robust platform for strong correlations. There's been lots of work done over the last few years. In particular, this tungsten diselenide, tungsten disulfide combination is quite popular, and one of the reasons is because, as Alex Hugeli very nicely showed earlier today, you have these sort of robust moiré patterns that arise just due to the lattice mismatch between the two layers, and so you have sort of a large sweet spot where you have at least minimal reconstruction effects. The platform that we've been using is tungsten diselenide and molybdenum diselenide, where there's very little lattice mismatch between the two layers, and so we need to go to a larger twist angle in order to have a sort of more robust moiré lattice, and also we don't anneal the sample and things like this. So we think, and we observe sort of moiré periodicities on the order of about 10 nanometers in our system. And I won't go into the details, but we've spent quite a bit of time sort of uncovering the behavior of these repulsive and attractive exciton-polarons as probes of the strongly correlated states, and we observe these sort of very strong magnetic susceptibility due to the interactions of the holes in these correlated states. And we can see, for instance, antiferromagnetic spin ordering, according to a Curie-Weiss model. This is very similar to work that was previously done, in particular from the Cornell group. But we wanted to build on this, and so today I'll talk about this hetero-trilayer device very briefly, with the idea then we're going to use absorption again, and we have sort of two types of probes. One is the exciton-polarons in the same layer, so it's looking at sort of, as we dope one layer, we can look at excitons absorbed into the other valley in that same layer, or we can look at sort of the excitons in a nearby layer. So there's sort of a lot of effects that arise due to these correlated states. So here's an example of sort of the hetero-bilayer sample that I previously mentioned. I won't go into the details. It's very similar to sort of what Alex Hugeli talked about, where we have sort of the absorption due to associated with resonances in the molybdenum diselenide, and then peaks arising in the tungsten diselenide. We understand a good deal of this picture. Some details we don't quite understand. But the nice thing is then if we take the same system, so we again have just a single moiré interface, and now we have this 2H tungsten diselenide stacked on top. We see the same features in the molybdenum diselenide that sort of reproduce what's seen in the hetero-bilayer system. But now in addition, we have an additional peak in the tungsten diselenide. And so, so we have this additional peak that arises because we have non-degenerate excitons in these two layers, because they have different dielectric environments. So one has a boron nitride nearby, and the other is sort of sandwiched between the two TMDs. In addition, we can see that the outer layer is brighter because the inner layer has a sort of fast charge transfer effect at the hetero interface. So it's a weaker, I don't know if you guys can see it back there. It's a weaker intensity just due to fast charge transfer. But nevertheless, we can see these two largely track each other, at least for a good amount. And what I want to focus then on is sort of the features in spectroscopy that arise of these exciton-polarons, in particular when we dope into the valence band in this hetero-trilayer region. So the first thing we can see, so I've just sort of zoomed in on that same region, so we're now going from 0 to -3 or greater, adding holes to the system. This is holes per moiré site. And we, again, turn on the magnetic field and we look at helicity resolved spectra. So the first thing we can see is that the spectra are identical, so we have no spin polarization. And the other thing is that we have a very clear red shift with increasing carrier concentration. So this arises due to this phase space filling effect that I talked about earlier. And both of these signatures sort of indicate that we have doping somewhere else than K. Simulations say suggest it's in the gamma valley, and I'll talk about that in a minute. And then as well, we see that the exciton-polaron doesn't actually form until one hole per site, and this is due to the fact that our exciton sits at a different spatial location to where our hole is doping in this gamma valley. So we can take the same data, and instead of performing a derivative with respect to energy, we can perform a derivative with respect to gate voltage, and then we see all the effects of the sort of correlated states appearing more clearly, and we can see all these sort of integer and fractional states appear. And we can assign then, and so this is just the same data as here, just taking the derivative with respect to gate voltage, and we can assign this due to holes going into the gamma or K valley. And what we find is that there are two inequivalent sites in the gamma. So there's like an A and a B site in this gamma honeycomb lattice that look like a sort of a charge transfer insulator. And so first we fill up the A site, we see these correlated states, and then we fill up the B site, and then we see, as I said, no filling in the K valleys, as we can distinguish from the exciton-polarons. And we see, again, another sort of deeper moiré band at the gamma, we believe. But then what we can do is apply the electric field and polarize all the holes into that are confined then into the outer tungsten diselenide layer. And in this case, then we see a drastic change in the exciton-polaron behavior. So now we have these strong, exceptionally strong spin polarizations and blue shifts rather than red shifts as well. And based on this, then we can say that we've now reordered our K-valley of that outer layer to be in between the two gamma sites, the energies of the two gamma sites, A and B in equivalent sites. And you can see then that the inner layer, the sort of heterointerface layer of the tungsten diselenide exciton-polaron barely changes. If we now look at the fractional filling of these lattices, we see these new states now emerge between 2 and 3 holes per moiré unit cell. And so we again assign this the filling of these moiré lattices, of these sort of moiré orbitals, I should say. So again, we fill first the A of the gamma, and then we fill the K, and then we go back to filling the B site of the gamma, and then we fill the K again. So in this case now we have new sort of metal to insulator transitions appearing at the higher number, at the higher filling factor. You're still sitting down, that's good. Okay. So the other thing we can, okay, including questions, right. So just to say we can look at the magnetic interactions again using our K-valley excitons as probes. They're only susceptible to the magnetic interactions happening in the K-valley, so we can't probe the gamma valley in this case. And we see these large enhanced G factors due to the magnetic susceptibility, we believe. I won't go into details for that. But maybe what gets more interesting is, so before I showed that we could sort of apply a large bias and move this K-valley in between the two gamma points, we can also make these two nearly degenerate, right? And then interesting things happen when we move these to degeneracy. So in this particular example, apply a bias between these two extremes, and we see again spin polarization of the exciton-polarons in the outer layer, as we expect. And this indicates that we start to fill the K-valley. In addition, we see some features that are not shifting at all, or maybe even slightly red shifting, which indicates that we're also filling the gamma valley. So we have sort of two species of exciton-polarons. And then when we reach a fractional filling of 2, everything collapses to one state where all the K-valley excitons transfer back to the gamma orbital. And in this case then, we don't have a good handle on the exact model for this, but it's due to some sort of interaction-driven redistribution of carriers spontaneously into the other orbital. So I think just to summarize, we've observed sort of this honeycomb lattice in the gamma valley and a triangular at the K valley for this sort of heterostructure. And as I said, the excitons at K valleys are excellent probes of correlated states in all valleys, but they're insensitive to the spin ordering in the gamma. So we need a different way to probe that. And we find that this gamma valley orbitals exhibits a charge transfer insulator, and then we have this sort of E-field tunable control of the system. So with that, I'll just repeat the 3 key messages, and thank you for your attention.
Thank you very much for the interesting talk and staying on time. So we have maybe a room for two questions. Yes. Ooh, so far away. Okay.
And thanks for the excellent presentation. I just want to confirm the first 2 points of your conclusions about the K-point excitons and their influence on correlative states. And are you able to completely eliminate the gamma point and have completely not hybridized excitons in this material combination?
So to do that, you can either apply a field of the appropriate field strength so that you can have, if I skip ahead a slide or two. So basically the DFT shows in this system, the two gamma-derived moiré bands are at higher energy and the Ks at much lower energy. So we can sit in this sort of position. If you go to sort of the monolayer position, then the K-valleys are sort of ordered on top. And then you also have the selectivity of the electric field in this device. I'm not sure if that answers your question.
Is this theory or experiment?
Well, this is theory, but it's consistent with our experiment, I guess.
But you always have a hybridization if you have WSE2 and MOSE2.
So there's always gamma valleys becoming relevant when you have more layers and you have interlayer coupling.
Yeah,
I think that's the simple answer.
Yeah, we also see cases where the gamma valley is completely absent, but not in this combination of material, and without the need to apply any external field.
Okay.
But anyway, we can discuss later.
Okay.